Hello everyone, my name's Logan and welcome back to the lecture hall. Today we're covering section 11.1, sequences, because I didn't want to do trig substitution today. That'll be the next video. So what is a sequence? Well, it is a list of numbers in a definite order. Essentially, well, what does that mean? Well, a sequence has to be ordered properly, and it's usually, you can have finite and infinite sequences, but it's just a ordered list of numbers. So we can denote them like these curly parentheses thingies, a1, a2, dot, 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 an, or we can just put the curly parentheses around an, or we can do it from an with the parentheses from n equals 1 to infinity. Or if your thing is only like, your sequence is only 20 digits long, then it's from 1 to 20. But typically, we have infinite sequences. So, well, what is one example of a sequence? Oh, well, my favorite one, and the one most people would know, would be the Fibonacci sequence. So it states that f1 equals 1, f2 equals 1, and then fn equals fn minus 1 plus fn minus 2. So, what does that kind of look like? Well, we got the first two entries. 1, 1. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 8 plus 5 is 13, 8 plus 13 is 21, and so on. And any Summerhawks watchers here would remember doing this activity to see whoever got the most Fibonacci numbers. So this section has just a ton of definitions and theorems, and we're just going to try to blast through them as fast as possible with some jump cuts. So we have definition 1. A sequence an has the limit L, and we write the limit as n approaches infinity of a to the a sub n equals L, or an goes to L as n goes to infinity. Right? And so essentially we have our sequences, and if they converge to a definite number, L, then we say our sequence is convergent. If they do not converge, then our series are considered divergent. We may have a sequence that goes 1, negative 1, 1, negative 1, 1, negative 1. And that would be a divergent series, right? Because it doesn't ever approach one number. We could have another one where it is maybe x, or x squared, an equals x, or x squared, where it goes to infinity. That would be a divergent series. We also have examples of convergent series as well, that we will be seeing later in this video. Now we have the epsilon definition of our limit, and this goes more into real analysis, and I'm not going to jump into the proof, but it's just a little taster for when I eventually come out with some analysis videos. We have definition 2. The sequence an has a limit L if for every epsilon greater than 0 there exists an n such that n, small n is greater than big N, then a to the n minus L, I guess the absolute value of a to the n minus L is less than epsilon. And essentially what's that saying? Well, as your number n gets big enough, sufficiently large, that the space between L, which is our limit, and an, which is our sequence approaching the limit, gets so small that it, approaches 0, or is a number less than epsilon. Our first of many theorems for this video states that if the limit as x approaches infinity of f of x equals L, and this is our function f of x, and we have that f of x equals a d n, where n is in z, essentially where what that means by n is in z, it means n is in the integer values. So essentially if our function takes only integer values, not rational or irrational numbers, and the limit equals L, then the sequence also converges at L. For definition 3, we have another analysis looking thing, and essentially this says that the limit, if the limit n approaches infinity of a to the n equals infinity, what does this mean? Well, it means that for every, this upside down a means for every m there exists, this backwards e means there exists, an n such that if n, the small n, this sub n is greater than n, then a to the n is greater than m. So essentially what this means in like real person words, is there will always be a number such that a to the n is bigger than that number, which is this m, depending. So essentially what that means is our sequence is always getting bigger and bigger and bigger, and then it will go to infinity. For our next theorem, we have the squeeze theorem, and we've seen this before, but we've seen it before in terms of functions and taking limits, and then we want to see, okay, well, what is it for sequences? Well, it states if a sub n is less than or equal to b sub n, which is less than or equal to c sub n, for all n in the sequence, and the limit as n approaches infinity of a to the n is equal to the limit as n approaches infinity for c to the n. If they both equal L, then the limit as n approaches infinity of b to the n also has to equal to L. And this is the same squeeze theorem, essentially, that we know for function limits, but it applies to sequences as well. And this is a good time to note that, well, all of our sequences follow the limit laws that I covered in, it was like section 2.5, short-haired Logan, at his college apartment Logan, where it's essentially you can add functions together, or if you add functions together, their limits add, multiply, subtract, divide, and all that sort of stuff. We have theorems 3 and 4 of our sequences video, and this states that if the limit as n approaches infinity of the absolute value of n, a to the n, or a sub n, equals 0, then this means that the limit as n approaches infinity of a sub n equals 0. And this can be helpful when we eventually get to finding where sequences converge, and how to do this is if we can show that the absolute value converges at 0, then we know that the sequence itself has to converge at 0. Theorem 4 states that if the limit as n approaches infinity of a to the n equals a sub n equals L, and the function is a function f of x is continuous at L, then the limit as n approaches infinity of f of a to the n is equal to f of L. And so essentially what this is saying is we're showing that the composition of limits still gives a limit. It still follows through the property. You don't have like chain rule or something that you have to do if you were to take the derivative of a composition function. It will just take it and it'll be the same. Theorem 5 states that the sequence r to the n is convergent if r is greater than -1 and less than or equal to 1, and it is divergent for all other r's. So any r that is not in the interval -1 to 1, where -1 would be a parenthesis, not a bracket because it's not included, if it's not in that, then it's divergent. So essentially what this is, and then what we have is the limit as n approaches infinity of r to the n is equal to 0 if r is between -1 and 1, but not equal to either of them. And then if r equals 1, then our limit equals 1. And that makes sense, because if we just replace r with 1, well then that would be 1 to the n, and 1 to any power is always going to be 1. So we have definition 4, and it states a sequence is increasing if, for every n in n, a to the n is less than a to the n plus 1. And what does that mean? Well, our numbers get higher as, our sequence number goes up. And then a sequence is decreasing if, you guessed it, for every n in n, a to the n is actually greater than a to the n plus 1. And so that makes sense, right? It's decreasing, numbers are going down. The previous number is going to be larger than the following number. Our final definition of the video comes with what is boundedness. So a sequence is bounded above if there exists an m such that a to the n is less than or equal to m for every n greater than or equal to 1. So essentially what does that mean? Well, there's some number that is always as big or bigger than every single number in the sequence, and that's bounded above. A sequence is bounded below if, you guessed it, there exists an m, we denote this as lowercase m because it's smaller, such that a to the n is greater than or equal to m for every single n greater than or equal to 1. So essentially, same thing as bounded above, except now it's below, and essentially this lowercase m is the smallest your sequence can ever be. So, last theorem before we get into our practice problems, the monotonic sequence theorem, and it states that every bounded monotonic sequence is convergent. So that's all well and good, but what does it even mean to be monotonic? Well, a sequence is monotonic if it is either bounded above or below. Alright, so that is all the theorems and definitions that I wanted to get through in this video. Let's transition to some practice problems. So for the first two practice problems, we are going to list the first 5 terms of the sequence. So we have a to the n is equal to 2 to the n over 2n plus 1. So all we do is plug in 1, 2, 3, 4, and 5 to find the first 5 terms, and well, we get that this is equal to, well, 2 to the 1 over 2 times 1, so that's 2/3. And then, well, we plug in 2. Well, we have 2 squared, which is 4. Over, well, 2n plus 1, well, that's going to be 2 times 2 plus 1, which is 5, over, well, if we notice, this just means an odd number, so it's every odd number, so then that's going to be 7, and then this one's going to be 9, and that's going to be 11, and then we just do powers of 2, so this is 2 cubed, so that's 8, this is 2 to the 4th, so that's 16, and this is 2 to the 5th, which is 32. So we get that the first 5 terms of 2 to the n over 2n plus 1 is equal to 2/3, 4/5, 8/7, 16/9, and 32/11. Now, we have a little bit weirder looking one. It kind of looks like a Fibonacci sequence, but it's actually not going to be. We have a1 equals 2, a2 equals 1. We need to find up to a5. Well, we have this strategy or series, sequence, not series, that'll be soon. An plus 1 is equal to an minus 1. So then if we have a2, we have a2 minus a1 equals a3, then a3 minus a2 equals a4, and then a4 minus, a3 equals a5. So we know what 1 and 2 are, and we just need to find the first 5 terms. So we plug that in. Well, that's 1 minus 2, which equals -1. And then we have 3 minus 2, a2, which is 1, which equals -1 minus 1 equals -2. And then we have a4, well, that's -2 minus a3, so that's plus 1, right? Because minus a -1 plus 1, so then we get this is -2 minus plus 1, which equals -1. And then if we actually continue this out, we see that it goes 2, 1, -1, -2, -1, and it continues. It never converges, but it all just stays around 1 and 2s. And, well, the absolute values of those as well. So the last one we're going to do, because, well, I've taken enough time filming this video and my roommate wants to, watch TV. We're going to do number 27, and what it says is figure out if the sequence is convergent or divergent. And so we kind of look at this, and we're like, okay, the numbers, well, we got a 3 to the n times 7 to the -n. We're like, well, how can we rewrite that? Well, this is obviously 3 to the n over 7 to the n, which is, we know, equal to 3/7. This marker sucks ass. Boom. Which equals 3/7 to the n. And then we're like, wait a second, we saw a theorem or definition, or something like that, where it said that r to the n is convergent for all r in greater than -1, but r is less than or equal to 1. So we look at 3/7, well, it's less than 1, so then it falls into this power sequence sort of deal, and we're seeing like, oh, well, this is definitely going to be convergent, and it's going to be convergent lim as a to the n, as n goes to infinity, well, this is going to be equal to 0, right? Because we said that if r is between 1 and -1 but not equal to either of them, those limits always converge to 0. I guess I should say series always converge to 0. Okay, well, this was a long video, and I know there was just a lot of theorems and stuff, but we have to get through that sort of shit so that we can get to the cooler math, we can get into sequences, we can get into Taylor series, and all that fun stuff. So, as always, my name was Logan. Thanks for watching. Have a great day.